Okay, section 6.4 is called transformations of these exponential and logarithmic functions. We just had a rather lengthy discussion about the relationship between exponents and logs as far as their graphs go. They are reflections over the line y equals x because they are inverse functions. And so the domain for an exponent and a range for an exponent switch places here if we don't move it around anywhere. Now we're going to transform them. And to transform these things, you have to remember generalized transformations of functions. And I think with this little discussion we had here, you pretty much got it. I'm just going to reaffirm some of the things that have supposed to have been brought to your mind as we looked at these things. So this isn't for these right now. I'm going to come back to these. I'm going to leave the graphs there because I want to refer to them in a minute. But for functions in general, if the function is f of x, then what does this do to that function f of x? It does if you're going to plug it into a function. What does this, if f of x is a graph of something, I don't care what it is, what will this one do to that graph? Yeah, it'll move it left 4. Does that look familiar to you? Yeah. And by the way, the reason I'm just putting f of x here instead of something specific is because I don't care if the function is a quadratic, linear, absolute value, exponent, logarithm, I don't care what it is. Doing this to it, replacing every x in it with x plus 4, as you said, we'll move the whole thing to the left 4. Right? I mean, correct? Okay. And this, we'll move it right 4. So you got that down. Okay. So this one right here we'll do, let's see, if I do this, f of x, and I go plus 5, we'll move it up 5, and this will move it down 5. So you got the up, down, right, left? Yeah? Inside? Okay. We'll show you what that actually looks like with respect to these in a minute here. I think you've seen some that I just erased there, but we're going to do it again. So this is up, down, or this is right, left, this is up, down. And then what does this do to it? Reflects over the x. Don't just write x like we say. That's what comes out of our mouth, but you have to put axis here. I have to know that means an axis. So that'll reflect over the x. What does it look like to reflect over the y? Yeah, it's the x inside that gets the sign change. Not the y values. The y values don't change sign. It's the x values. So they're on the inside. That'll reflect over the y-axis. What other transformations do we need to discuss? Stretches and shrinks. So what does this do to it, for example? What kind of stretch? Vertical stretch. Of 3. So this would be a, well, let's make it a little more fun.
Shrink.
What kind? Vertical shrink. You better use at least an H here. Some people put VS, but guess what? Stretch and shrink start with S. Don't do that. You got to indicate which one's which. This is a vertical shrink of 2/3, yeah? Yeah. Okay, those are easy. This last one, you got to remember, if I do this to it, what's that? Horizontal shrink of half. Good. And if I do this, this is an interesting one.
That's a vertical. Horizontal.
Horizontal. Will it be a stretch or a shrink? Why? Why is it a stretch? And the reciprocal is, which is greater than 1. 5/4 is greater than 1. So when you flip it over, if the number you flipped over, the reciprocal of this is greater than 1, you'll have stretch. So you have to think reciprocal when it's on the inside, right? This is all old news, right? All right, so let me show you what it's going to look like if I actually identify this function up here as, let's say, e to the x. That's your typical exponential function. It could be 2 to the x or 10 to the x, as I demonstrated for you before. So if I want to move this function to the right 8, then I want to do this to it, right? As you said, as we started out, that means replace the x with this. So you should be able to recognize that as being, as from the parent e to the x, as being a shift to the right 8, because it's in the exponent. This is where x is x that gets replaced with x minus 8, and that right up there, up here, is going to be a shift right or left. Y'all see it?
Yeah.
If I want to move it down 4, that means this. That means it's still f of x. That still remains, but then minus 4 after you exponent. So it's on the outside of the function. You follow me?
Yeah.
The functioning here is exponenting. And so the functioning did not change. We just, after we did the functioning, we went down 4. Okay? If I want to, let's say, vertically stretch it by 2, that would look like this. That would be this. If I want to vertically or horizontally stretch it by 4, that would be this. Right? Vertical or horizontally stretch it by 4. That is a replacement. That would be e to the 1/4 x. Which, by the way, and you need to get used to it, is the same thing as e to the x over 4. Do you recognize those as the same expression?
Yes.
See that 1 right there? That's written right there? 1/4 x. That's going to be your, that tells you what your stretch or shrink is. And since it's affecting the x and not the e to the x, but affecting x, it's going to be a horizontal something or other. You following all this? Okay. What if I want to reflect it over the x? If do something like this. That means that the entire function, e to the x, gets a negative on it. That's going to flip it over the x. It's going to be a vertical because it's on the outside. Okay. How about this one? If I do f of negative x, that's a pretty easy one. That's going to be e to the negative x, which is going to take this graph and flip it over the y. It's going to make it a decay. It'll come down this way instead. If you flip it over the y. You following? Now, let's see if we can do several of these at once. For example, do you have an idea how you might graph f of, let's call it g. So I don't think it's a parent function. I've always referred to those as f. If I have a g of x function that looks like this, negative 1/3 e to the negative x plus 1. That's a rough one. Can you describe the transformations and then maybe we can put a graph together?
Yeah.
What is this going to do? Pardon?
Is the negative part a reflection?
Yes, but which negative?
The one before the 1/3.
Okay, and that's that one before the 1/3 is going to reflect it how?
The x-axis.
Yep. Okay. Give me another transformation.
Vertical shrink of a 1/3. Is that a +1?
This is a +1 right there.
Left one.
Nope.
Oh wait, no, hold on. Right one.
Right one. And I'll show you why in just a minute, but it's going to be a right move. You're going, yeah, it is. I'll show you. Right one and
Reflection in the y-axis.
it's going to do both reflections.
Oh, so would those just like cancel out? And in front of the x.
They don't cancel out. The reason why it's going to go right one, and this is usually the clincher for people. They're going, I don't understand that. This is tricky. A rewrite of g of x could be written like this. You cannot read this for a right-left move unless x stands alone in front of it. And I mean alone. No negative, no nothing on it. So what I did is I factored that negative, the negative 1 right there on that x, I factored it out. And when I did, I had to take it out of that positive 1 as well. So that if I were to redistribute it, I would get negative x plus 1. I factored out a negative is what happened. You see what happened? You see that? Now that this stands alone with an understood 1 right there, not a negative, not a 2, not a 1/2, but a 1. Now I can read this for a right-left move. This is going to go right 1. And this is going to make it reflect over the y. Tricky. Y'all see it? You cannot read your right-left move unless x is all alone with just a 1 in front of it. And if whatever you have to do, whatever you have to make that happen, you yank that out front. I'll show you another one here in just a minute. But let's see if we can figure out what this looks like compared to this black one right here. See if we can figure out what that thing's even gonna look like. Now, I don't care that you get the right bend in it. That's gonna be tough. And the 1/3 is gonna be affected by that. It won't be quite as fat. It's gonna be a vertical shrink, which we decided. It's gonna squeeze this down and make it go out wider. But I just want an indication of that. But it's these reflections. This one's gonna move it to the right one. It normally crossed at, the normal parent function crossed at 0, 1. You remember that point right there? Mm-hmm. Well, if you pick that point up and move it to the right one, we're now going to be going through the point 1, 1. Well, actually, 1/3 because of that shrink. It's kind of tricky. So this line right here has been moved over to the right one. That's this one right here. It's also going to reflect over the x and also reflect over the y. We'll take care of those one at a time. The reflect over the x is good. It normally went like this. You see that the reflect over the x is going to make it go like that? Yeah. Okay. So I'm going to put a dotted line here. It's going to reflect like that. Now I got to take that guy, and it doesn't matter which one you do first or second. I got to take that guy and flip it over this way, which means ultimately the graph is going to look like. By the way, this is going to reflect also. This point that I had there, it's going to reflect down here, and it's going to hug this x-axis over here like this, and come down like that. Crazy, right? That's a lot of stuff right there. A lot of things to consider. Okay, let's try one more exponential one, then we'll do a log one. They're not that hard either. Once you see the exponents, it's going to be not too bad. You'll see. So let's see about this one. This will be about the worst case exponent what you're going to have. If I have a function that's been transformed, I have g of x equals -2e to the 3x minus 7. Ooh, gross. See if we can identify the transformations on this. But let's first do what we said before and get this x to stand all by itself, all alone. It's not right now. It's got 3 sitting on it. We got to get that 3 pulled out. So I'm going to rewrite this thing as -2e to the 3 parenthesis x minus, anybody? Don't get your calculators out. This is an easy thing if you understand what you're doing. I don't want a decimal. See, what's happening when you factor a 3 out of both of these is you're dividing them both by 3. If you divide this by 3, you get x. If you divide this by 3, you get 7/3. Ugly, but still, that's what you get. So that if you redistribute, you take 3 times x, you get that 3x back. If you take 3 times 7/3, you get 21/3, which is 7. See what I mean? That's just verification that you pulled it out correctly. So now that we've written it like this, and this x does stand alone right there, can you identify the transformation? Anyone you want.
Vertical stretch by 3.
Is it?
Horizontal shrink.
Horizontal shrink of 3. Of 1/3, excuse me, 1/3, yeah. That's a tough one to see, but that's how that one works out. That 3 is up there associated with the x and the exponent. So it's going to be a horizontal thing, the opposite of what you think. What else? Reflect over the x.
Right 7/3, right?
Right 7/3, very good.
Vertical stretch by 2.
Yep. Is that it?
I think so.
It is. Okay. So horizontal shrink of 1/3 means it's going to go this way. It's going to make it steeper. It's going to make it climb up faster. But it's going to be vertically stretched by 2, which is going to make it climb faster yet. This is going to squeeze it this way, and this is going to pull it this way. It's going to be a really steep little curve. It's having both effects of making it go up fast. It's also going to reflect over the x. So normally it goes like this. A reflection over the x is going to go like that. We don't have the other reflection, so it's going to hug over here and come down over here because it's reflecting that. You following me? I know. You're going, would you draw something? Not yet. And it's going to move to the right 7/3. 7/3 is a little more than 2.
Yeah.
So it's going to go over here. Here's 2. This point right that would normally have crossed right there. It's going to come down here. It's also a vertical stretch of 2, which is going to make it come down here. It's really About right there, it's gonna have to go through. And it's going to drop off hard from here because it's been stretched vertically and squished horizontally, so it's gonna drop off fast. I really don't care about that much, just that you place it in the right place and you make its asymptotic behavior on the right part of the x-axis. That's what I'm concerned about. Yes?
I just didn't really catch how you got like the low third.
It's this 3 right here is up here with the functioning part of this. It's in there with the x. You know, it's tied up with the x. And so this has to be a horizontal something or other. Whenever you've got a horizontal, it's the opposite of what you think. Because this was negative. When we went right 7/3, this is a multiplier of 3, so it's really going to be reciprocal of that. And it'll be horizontal.
Oh, okay, yeah, I see.
You do?
Yeah.
Okay. This one, though, is vertical because it's out front of the function. After the functioning's occurred, this is a vertical move. Exactly what you think when they're vertical.
Yeah.
You with me? Okay. Everybody okay with this? That's about as tough as it's going to get exponent-wise. When you deal with a logarithm, you just have to have this vision in your mind and transform it. And the very same things happen. I'm going to do, just for the sake of variety, I'm going to do a function up here, g of x, that is not a natural log, but let's say a common log. Let's say I'm going to do 1/2 log of negative, let's do it all at once. See if you guys can handle this all at once. Negative 2/3 x plus 4/3. That's crazy. That's a nutty one there. If you can handle that with the fractions and the negatives and all that garbage there, if you can handle this, you'll probably be just fine with this section. Do you want to do any rewriting before we identify the transformations?
Do we need to rewrite it as an equation?
It is an equation, but I think we need to rewrite it so that that x behind the log stands alone. Remember that little deal before we can read it?
Yeah.
Okay. All right, be really careful with this. This is going to be 1/2. That's not going to change. Log of
Well, 2/3 on the negative, so
negative 2/3, and then what's inside?
x
Minus 2. You guys are really good. For those of you that were talking, for some of you, I'm looking at your faces and you're going, that's a really hard thing to do. This is 2/3 comes out front here so that this can just be x. This is also going to change sign. That was a negative term, now it's positive. This was a positive term, now it's negative. Maybe you handled that okay. But how in the world do we get a 2? Remember that you're dividing by 2/3 or negative 2/3, which really is 4/3 times negative 3/2 if you're doing the fractional arithmetic. And these 3's cancel. And this 2 cancels for a 2. What are you left with? A negative 2. Did you catch that? Here's another way you can think about it that's a little more intuitive. 4/3 is twice 2/3. So if you take a 2/3 out of there, you'll have 2 left. 4/3 is 2 times 2/3. If you thought about it that way, that's great. Otherwise, you're going to have to think about actually dividing 4/3 by 2/3 and do this opposite reciprocal and cancel what you can. But you end up with a negative 2 there. Is there anybody who's still struggling with that idea? Anybody? Okay. So this is the rewrite of that. Now that we've got this x standing alone like we like, can you identify the transformations? Any of them?
vertical shrink by 1/2.
Okay.
Right 2.
Right 2.
Horizontal stretch by negative or by 3/2.
Good.
Reflection over the y.
Is that a reflect over the y?
Yeah. I think that's it.
Okay, now think this. Think this for parent. Now they all have this same basic shape. The only difference between different parent functions here is how quickly it goes up or down. And the bigger the base, the bigger the base of the logarithm, the flatter it gets. I'm not really concerned about that so much. But I do want you to realize that you've got a vertical shrink and a horizontal stretch of 3/2. That's going to make it really flat. We got both things working together on this. We're gonna flatten it out this way, we're gonna flatten it out by stretching it horizontally. It's gonna be double flattening. And we're base 10, which is already really flat. 10's bigger than E by a long shot. We gotta reflect over the Y. So, gotta try to account for all of these things. Let's see. I'm gonna reflect over the Y first. It would normally go like this. So imagine this. It would normally hug this tight like this and come out like this. I'm gonna reflect it over the Y, which means it's gonna hug here and come out like this. Does that make sense?
Yeah.
And it's going to go to the right too, which means the asymptote is moving over to here. You following me? And it's going to come out like this, and it's going to be, we got the right two, this is going to flatten it, this is going to flatten it, and we got the reflection by coming out this way, so it's going to be really flat. This is what I mean by really flat. It's going to come up like this, and it's going to turn hard and stay pretty flat. Oh, like that. You check it out. You want to graph? You can graph that thing because it's a common log base 10. Put that in your calculator and see if that isn't what you get. Let's try it. You're graphing, you can either graph it in this form or this form. I'm going to take these off. It doesn't matter which. This might be a little easier to put in, but your fractions have all got to be in parentheses. It's a pretty parenthesis-intensive little graph there. So try it. Check with your neighbor. See if you can get all this to happen. See if you can get that to graph properly with a bunch of parentheses. Are you able to? No? This is the syntax.
Oh.
Can't log a negative, but you can put a negative in there. It'll still work to serve as a reflection. So the syntax for graphing is, this is what I did. I just wrote 0.5 so I wouldn't have to put a half in parentheses, because that's the same thing. And then I typed in the common log key, and there was already a parenthesis slapped down. I put down another one so that I could put that -2/3 in parentheses, close that and put an X on it. That's this part right here. Are you with me? Yeah? You see what I did? Why I need a parentheses on the 2/3? I'm trying to write this, and you're going to put that in as a fraction. You're going to have to put it in parentheses. So I have 0.5, that's this half, log. And the log already made a parenthesis for me. I want another one so that I can put this in parentheses right after. -2/3, close that parenthesis, there's my X. Are you with me? Plus, and if I'm going to put 4/3 in, I'm going to need another set of parentheses, 4 divided by 3, close that fraction, and then close the logarithm. That'll be your syntax.
There we go.
Put it on a standard screen, and you get something kind of like this, except for it looks like this instead. This is what your graphing calculator does. It hugs it really close here, comes over here to 2, and drops off, and it just stops there. Do you know why that is?
Wait, where's the stop?
What? This is what I got on a standard graph. I don't think you can see that very well. It's just a little tiny hook at the very end on this side. And it doesn't drop off like my graph shows. You know why that is? Did you get something like this? You have to know, as the operator of the calculator and the understander of logarithms, that thing drops off and goes down forever, and there is an asymptote there. Even though it's hardly dropped at all in place. It's because immediately after it makes this corner, right there, it stops. There is a pixel. It's hard to demonstrate this, but if this is the y-axis, and I'm over here at, sorry, let's say that this is a line, which is the number 2. X equals 2, so the origin's way over here. Here's 2 right here. There's a pixel row in your grapher like this right here. And what your calculator does is it comes over, the graph's coming over like this, and as soon as it gets in this pixel row, the graph, the next point it wants to plot is also in this pixel row, a little farther to the right, but not by much. And the next one will be in that pixel row, and it says, oh, that's a non-function now. Because non-functions have vertical lines are non-functions, and this has, according to the calculator, has the same value more than once, and it quits after it gets the first one. It won't graph the next one because it's under very strict orders to graph only functions. And functions can't have the same x value over and over and over and over again. And that's how it perceives it. So it quits. You got to know that it quit for that reason and that there really is an asymptote there and the thing actually does drop off like this and hug that asymptote. It just perceives all of this as being the same x value and it refuses to graph it. You got to know that. That logarithms cover all bases. We're down asymptotically. It won't show you very much, especially if it's really, really strong. Okay, that was fun. Let's see what else I got to show you. If there's anything else, I don't think so. The only other thing that you're going to have to do is to take a list of transformations and write the equation that belongs to it. So we're going to go backwards. We'll try one or two of those. Okay, so take a look at example 5. Example 5 says, let the graph of g, a new function, let the graph of g be a reflection in the x-axis followed by a translation 4 units right of the graph of 2 to the x. I didn't do much graphing, so I guess it wasn't necessary to see that board. I'm going to use up this instead. Okay, so we're to write, this is what we're doing, the parent function f of x, 2 to the x, so that's an exponent. Parent function has a 2 in it, that's okay. That's our parent, and we wish to write a g function that has this list of transformations. It's example 5 on page 321 for those watching this. And we are to do a reflection in the x, and then a translation 4 units right. That won't be very hard. Anybody? How do we write a reflection in the x? Can we do that immediately? What are we going to write? Negative, and then 2 to the x. The other transformation's up here. Where do they want us to move it?
To the right, so -4.
What do you think?
Yeah.
Does that look right? Okay. When you're moving right-left, it happens up here with the x, because right-left is a horizontal thing, and horizontal things are tied up with the functioning. Reflection over the x is a vertical reflection. That happens after the functioning. Slap a negative on it, makes all your y values negative. That wasn't too bad. Let's try example 6. Let the graph of g be a translation 2 units up, followed by a vertical stretch by a factor of 2 of the graph of log base 1/3 of x. Ooh. So if this is the parent function, f of x equals log base 1/3, which is weird, base 1/3 of x, we are to transform it, do 2 things to it. Let's see if we can write them both at once. G says,
Did Rebecca show up?
Nope.
G be a translation 2 units up. Got an idea how you're going to make that happen? Think about that. 2 units up. Where? At the end after logging has happened, right?
Yes.
Because we're going up, down. 2 units up, followed by a vertical stretch of 2. Followed by. That may be a bit of an interesting thing. How do we do the first part, which is to go up, to say up to?
Yeah.
What does that look like?
Put your log to the base of a 1/3. And then that's the x, and then you'll just put the plus 2 on the end of it.
Indicating that it's not in parentheses, is not logging the 2 as well, right?
Yeah.
Okay. Followed by a vertical stretch of 2. In other words, folks, in a general way, what's happening here is we're saying that g is equal to f plus 2, and then we're going to vertically stretch it 2 after that. So really, it should be this. After we get it written here like this, and we do this first and then followed by, final answer will be something like this. 2 log base 1/3 of x plus 4 by distribution. You with me there? Okay. Think you can handle this? It's routine stuff, it's just that it's now being applied to something that's new and different. So on page 322, these are the exercises. For those of you doing it on paper, here it comes. Numbers 2 through 6, 7 to 29, odd, 31 to 34, 35 to 41, odd, 45 to 49, odd. It's 28 problems. That's quite a bit to do. You've got about 20 minutes to work on it in here. Let me know if I can help you. Bye.
I check my numbers.